If tomorrow somebody finds even a classical factoring algorithm in polynomial time, I think there'll be chaos in the world.
This is Avi Wigderson, Turing Award and Abel Prize winner, and I interviewed him all about his field.
The question of P versus NP is whether we can solve all the problems we really want to solve. The quality of randomness is in the eye of the beholder, or in the computational power of the beholder. How can anybody convince me that they have a proof of P different than NP, and nevertheless I know absolutely nothing about the way they proved it? And it turns out they can do it for the halting problem, for problems that are not computable. You know, if tomorrow somebody finds an efficient algorithm for an NP-complete problem, you know, what do you do?
Here's the full episode. In one of your lectures, you mentioned that P equals NP is philosophically about the fundamental limits of human knowledge. What is P equals NP, and how does it relate to human knowledge?
Well, in the simplest way, and I will talk at a high level, we are interested in various problems in life, in all sorts of problems, mathematical problems, scientific problems, medical problems, personal problems, intellectual problems. We are in the business in computer science of solving problems by computers. Now, we would like to somehow classify those problems that we can solve, right? To know what we can know. Well, the problems we can solve are the things we will know, we will understand. So there are all these problems that we want to understand. There are many of them. And there are the problems that we can understand, can solve, okay? In a very basic way, the first class is NP. All the problems we want to solve are really NP problems. So it's a class of problems. A subset of it is the problems we can solve. There are the problems we can currently solve, but we are interested in all the problems we can solve in principle, we can ever, really solve. So the question of P versus NP is whether we can solve all the problems we really want to solve, whether we can know everything we want to know. This is basically about the limits of our knowledge. Of course, I have to justify why these classes, which are mathematically defined, actually are captured by this intuitive meanings I'm giving them. P is very easy to justify. What we can solve is what we can, solve in our lifetime using whatever we have, let's say all computers that we have, using efficient algorithms. So problems we can solve are problems you see in our apps in our phones, right? If there's a navigation app, it means somebody invented an algorithm that's efficient enough to solve any, shortest path problem between any two places in any kind of map. Okay. While all the problems we want to solve are NP problems, what is NP? NP is a class of problems, the mathematical definition, are problems so that, whether they are easy or hard to solve, we don't know. But if somebody hands us a solution, then we can easily check that indeed it is a good solution. Now, why are all problems humanity is interested in of this nature? You can think there's no limit to what we may want to know. But I claim that essentially in any human endeavor, if you are embarking on any problem, if you really seriously want to solve a problem, the least you want to know is that when you hit upon a solution, you recognize it as a solution. I mean, why would you ever start on looking for something if you will never recognize it as what you looked for? So you think mathematicians are looking for proofs of theorems? Certainly if somebody gives a proof, wrote a paper about it, we can verify. If a scientist wants to explain data, about the planets or about, bacteria or whatever, want to develop a theory, so that's what you are searching for in this case. And yeah, again, scientists write papers about their theories. They have to be consistent with the data. We have a way of recognizing that this is a good solution. Engineers, are usually tasked with creating something, bridge or phone or, something under some constraints. It can be monetary constraints, physical constraints, all sorts of, you can use this but not this, and so on. But anyway, if an engineer designs something, whoever gave them the task can look at it and say, well, you violated some constraints, or no, it's good. You really delivered what we were looking for. So I'm giving you examples. I mean, I can give many more. Detectives are supposed to solve crimes, and, we know from detective books, they eventually provide. So these are examples of very fundamental human endeavors that are, encompass almost everything I can think of. In all of them, what people are searching for have the property that when a solution is found, it is easily recognized. So, repeating the beginning, NP are all problems that we can honestly say we really want to solve, and P are those that we can solve. Whether they are equal, if they are equal, then everything we would want to know, cure for cancer, anything you imagine, can be, just the very fact that a solution can be easily recognized would imply that it can be efficiently found. That means that we can know everything we ever want to know. It's a fundamental question about human knowledge.
So I know this is one of those Millennium Prize problems. There's $1 million prize if you can provide a proof for this. I can imagine you could prove that they're equivalent. You could also prove that they're not. If you had to guess, like when and if a proof comes, which direction would your intuition say it goes and why?
I think that my intuition, and that's probably holds for almost all members of the theoretical computer science community, is that they are different. I think there are several reasons for that, and I will already tell you now that they are not that convincing. One is, I think, intuition that most of us have, that, finding something is really hard than just checking that it's there. If you lost your keys or your phone and, you have no idea where to look, but, if somebody points out, oh, you left it on the windowsill or something like this, yes, yeah, I did. So we have this experience from life that finding is typically a harder task than just checking that it is what we look for. Another is that real NP problems occur all over the place. They occur in optimization, in logic, in other aspects in mathematics, in verifying that algorithms and protocols and security systems actually work, all sorts of. In this generality, these optimization problems that are NP problems, maybe NP hard problems, people try to solve for completely, egocentric reasons, to make their company richer or to, and there are thousands of these, and they manifest themselves in many different forms. And so over the maybe 50, 60, 70 years, people seriously looked for algorithms for these very different ones and couldn't find any. This, may seem like there's no such solution. And in getting a bit more technical, NP problems, NP complete problems in particular, seem to require search over an exponentially large space, like all the possible, solutions to some system of equations, for example. Somehow P versus NP is about having a general method for cutting down this exponentially search space into searching over something much smaller in a clever way. And this should apply to all these problems. So that would be P equal NP, and people don't think that there is such a way. But as I said, these are, these are intuitions that are, maybe pretty strong. And I think that's the only, if tomorrow somebody finds an algorithm an efficient algorithm for NP-complete problems, using some new idea that nobody ever thought of, what do you do?
That would change the world. In software engineering, we use algorithms all the time, and they often have these very satisfying properties where the solution, we use space or some algorithm that can take something where the brute force is something much larger down to something that's polynomial time or something very reasonable. But in all these NP problems, it's pretty unsatisfying that the best we could do is brute force. Am I understanding that correctly?
Yeah, you're understanding it perfectly correctly. I think that maybe what you are getting at is that NP-complete problems are, a particular NP-complete problem is really a family of instances, right? I mean, you want to find a Hamiltonian tour, some traveling salesman tour through some map. There's this map and this network and other network, and there are many, many instances. When we talk about an algorithm for them, typically we say an algorithm is efficient if it's efficient and correct on all of them. In software engineering and many aspects of optimization, in many real-world problems, the instances is a much more restricted set. They come from, trying to verify a particular protocol, or, protein folding, if you want to think about a biological example. The way it is phrased as an NP, our problem is you want to minimize the energy of a system under some various constraints which have to relate to the chemistry of the various molecules and atoms that appear in the protein. And this kind of optimization problem, one can easily prove, is NP-hard. And nevertheless, our body folds our proteins all the time, in extremely efficiently. Now, why is that? Of course, I don't know really why is that, but it would seem that evolution designed proteins in such a way that these, folding them, only them, we don't have that many proteins. There are not exponentially many proteins in the body. There are only a few that maybe are more prone to efficient energy minimization. So, and more generally, I think in software engineering, or at least in verification and testing, you often want to check that something meets the specifications. You usually translate it into a satisfiability question of Boolean formulas. The formulas that you get, the instances that you get out of these, have some structure, and maybe for them, various greedy approaches or clever, not just greedy, but clever but efficient methods work. In other words, making it short, instances that come up are not the worst case instances. We have many examples of this that we can actually prove this. For example, early on it was recognized that the simplex method, which is an algorithm to solve linear programs, on the one hand, requires exponential time for, worst case system of inequalities, but in practice, it seems to run in linear time. So evidently, the sets of linear systems that we tackle in real life are, have some extra structure that allows this particular algorithm to solve them efficiently. Of course, today we know an algorithm that's efficient for all linear programs, but it's much more complicated, and people don't, or I don't know how much it's used in practice. But the simplex method is a very simple to run, and usually it works.
You mentioned the protein folding, and I mean, yeah, that's an interesting one because it's an NP problem, but it was solved to an acceptable extent. And when I was reading about it, it wasn't solved for 100% of cases. It provides a solution and a confidence score, but it doesn't give you the answer 100% accurate, fully computed. And so when you think about these NP problems, what if you relaxed the criteria of being correct? Could the asymptotic complexity be less than the exponential that we're talking about?
Yeah, it's a very natural and good problem. So in the protein folding, you were talking about 𝗪𝗵𝗆, I guess, which is an algorithm, a heuristic that was learned from existing proteins and is working very well on instances it didn't see, but are still proteins coming from the body. Even if it did perfectly on these, not just that would still fall in the discussion I mentioned before, because the instances it is trying to solve come from real life and probably have extra structures that allow efficient solution. But you are right, that's one of the things that people naturally do when they cannot solve an optimization problem exactly because it's NP-complete or NP-hard. Maybe I should say NP-complete, NP-hard problems are those problems in NP that are as hard as all problems in NP. If you solve one efficiently, you solved all efficiently. If you prove one hard, then you proved all of them hard. So they somehow capture the complexity of the class, and traveling salesman is an example, and protein folding in this framework of energy minimization is one, and Boolean satisfiability, and so on. Okay, so you want to optimize something, and it's NP-complete, NP-hard. So that's a sign that you shouldn't try to find an algorithm that works always. But one thing you can do is do an approximation. That's a very natural relaxation. You don't want the optimum. You are willing to live with a factor of 2 from optimum, or 10% from optimum, or some factor away from optimum. NP-completeness was discovered in the early 70s. In the early 90s, there was a breakthrough called the PCP theorem. The PCP theorem allows you to argue hardness of even approximation problems. So, for example, you can show that satisfiability of Boolean formulas, is not just so you want to let's say find an assignment to a bunch of constraints, let's say Boolean constraints, let's say on 3 variables for simplicity. So you want to satisfy all of them. The relaxation would be, okay, I want to satisfy 90% of them, or as good a fraction as I can, if I cannot get 100% of them. The PCP theorem, one way to phrase it, and certainly one of the major consequence, is that we know that you cannot even achieve a very good approximation. And to illustrate how tight this understanding is for some problems, is that for the example I gave, when there are only 3 variables per constraint, if you just guess at random the values to the variables in the assignment, you will satisfy 7/8 of the constraints. This is because each particular constraint is usually the disjunction of 3 variables, will be true with probability. It's an OR of 3 variables, will be true with probability 7/8. So if you random, if you don't look at the formula even, you can satisfy 7/8 of them. And the PCP theorem and the significant strengthening by Johann Hastad tells you that if you want to satisfy 7/8 plus epsilon, that's already NP-hard. So we know today to argue the difficulty not only of finding the perfect solution, the optimal solution, but even how close to optimal you can get for lots and lots of problems, large classes of problems, in particular constraint optimization problems, of the type of satisfiability.
So even if you solve just the slightest epsilon for any trivially small epsilon, it's just as hard as doing the full.
It's as hard as finding the optimum solution.
You mentioned NP hard, NP complete, NP-P. I know there's other complexity classes. Maybe you could give some more context on kind of the whole space of complexity classes.
Yeah, so I'll just remark that we have a zoo of complexity classes. In fact, there's a website called the Complexity Zoo, which has in it hundreds and hundreds of complexity classes of all types. Website started by Scott Aronson. Once we realized that he realized there's a whole zoo out there. We want to know the relationship between these classes. Okay, so what is the point about these classes? Like P and NP, we want to classify problems by the amount of resources they take. So P, polynomial time, is a class of problems that can be solved in an amount of time that relates polynomially to the size of the data. Of course, you expect that there's more data, the instance grows, you'll spend more time. But if it's linear time or quadratic time or cubic time, you say, let me call it at least theoretically efficient. And NP, you classify not the time to solve, but the time to verify a solution if it was given. You want this to be a polynomial time. So it's a very different. But first of all, there are many more time functions than just polynomial and exponential and doubly exponential, and you can go to finite. And one fundamental result, starting with Turing's paper, is that there are problems that are simply unsolvable by computers. So really the first complexity class is a class of solvable problems, decidable problems. Turing showed that these are not all problems. There are natural problems that are not decidable at all. But time is only one resource. And we are interested, and both from practical and theoretical reasons, in lots of other resources. Memory is a resource, costly resource, and we want to minimize space. The space is invested in a computation. In problems with several parties, you are interested in the amount of communication exchange, so not the internal computational effort that they exert themselves, but how much. If you talk to a satellite, you want to minimize the communication. You can think about energy. You can think about, there are plenty of parallel time. How much can you speed up, computation of a problem if you work on it not with one computer, but with n computers? If your data is of size n, does it, allow it to solve it immediately, or maybe it doesn't help at all? So there are complexity classes classify problems according to how much resources they need, and there are many of these. And one important part so that's a major theme in the methodology of complexity theory. And coming with it is attempts to understand complexity classes as problems that relate to each other, even if you don't know their complexity. So, for example, NP is a class, and we don't know the complexity of all problems in this, or NP-complete problems. We don't know whether they are all easy or all hard. But we do know we have efficient algorithms to translate one into the other. So it's not obvious that if you want to solve a satisfiability problem, you don't know how, but you have an algorithm to solve Sudoku problems, large, not just 3x3, but also 4x4. If you had an efficient method to solve Sudoku problems, P equals NP, because you can efficiently take an instance of satisfiability or traveling salesman or factoring integers or any of these problems, build from it a Sudoku problem. And from the solution of the Sudoku problem, you can translate back and get the best solution for your original, traveling salesman tool. So we are interested in efficient reductions between problems whose complexity we don't know, but we want to relate them to each other. We build some kind of partial order of the hardness of different problems. So there are, really, you don't want to know how many problems we have. Some arise for constraints that the real world, maybe technology, imposes or calls for, and some are naturally arising mathematically because, they are interesting.
You mentioned that these NP-complete problems, they kind of are all equivalent in some way.
Yeah.
What's the proof to, equate a SAT solving problem to like a graph coloring problem or something like that? Are they all similar in nature, or are they kind of bespoke to, the problem you're going to and from?
It's a very good question, and you will find that in most of these, they call them reductions, algorithms to translate one problem to another. Most of them are relatively simple. And not all, and I talked about the PCP theorem before, showing that approximation is how this is very highly non-trivial. But most NP-completeness proof, like between coloring and satisfiability, and it goes both ways. They are both complete, so it goes both ways. It is simple, and the first one was the satisfiability problem. The original papers of Cook and Levin defining NP-completeness and proving that NP-complete problems exist. They both, the first problem they proved complete was satisfiability. Why is this? So why can all these other problems be reduced to satisfiability? The reason is really that computation is local. Computation is local. I mean that if you think about your computer, your laptop, or any computational device, usually it manipulates bits by some local operations. You look at these two registers and you add them, or you take these two bits and exclusive OR them or AND them or something. And you do a sequence of simple operations, and you arrive at a conclusion. This locality can be translated to a bunch of constraints, or what will be consistent sequence of states of your machine. If you look at the time evolution of any computation, memory is in some state, then in another state, but they change locally. Okay, so if you could guess, and that's the NP part, if somebody provided you the table of computation, you could check that it's consistent by writing a bunch of local constraints, so, some conjunction of very few variables all over this table of computation, and write down a satisfiability problem. I want this to be true, this to be true, and this to be true for some assignment. And what does the assignment has to satisfy? It should be a table like this. All these constraints should be satisfied, should be true. And it has to be consistent with the input given, right? So some of the input has to match the first times zero content of the machine. So this locality allows for many of these translations. If you realize this, you will quickly find a reduction from coloring to satisfiability. It's also, it's not clear why coloring is an evolution of computation, but it starts already by local constraints. You want a few colors, and that in some it's even easier, but the reduction from any NP computation, that's what NP completeness means. Anything in NP can be translated to satisfiability. NP is just a computation of a Turing machine, say, only that you don't know what is the computation. If somebody guessed it or showed it to you, then all you need is to verify it. This verification is local. And that's the source of many simple, NP completeness reductions. Let me give you a really simple example. Why is factoring integers reducible to certifiability? Because if I gave you factors of an integer, you could just multiply them and check that they equal the input. This multiplication is a simple algorithm, right? I mean, we know how to do it from second grade or something. You write down the computation of multiplication in this local way. And all you need is that somebody will guess for you really the factors.
You mentioned time complexity and space complexity, and I think intuitively, like in software engineering, we often trade those off for each other. Is there like general theory on that, on how these two trade off?
Yeah, we have, all these questions are natural questions for complexity theorists. How does two resources relate to each other and whether they can trade off, or maybe you can minimize them both at the same time. And it depends on the problem. There are problems for which we know results like multiply time and space. It has to be at least the square of the length of the input. So you can either do it with very small space like logarithmic space, but you need to pay maybe quadratic time. And if you want linear time, you have to pay linear space or close to linear space. There are results of this type in various models of computation. That's another thing you play with. Not all of them are, they're all equivalent in principle, but if you care about exact time or exact space, they are not equivalent. So there are problems for which there is a trade-off. There are problems for, where you can solve them in linear time and logarithmic space. One very important general result that is a breakthrough from last year is a result of Ryan Williams. And I'll tell you what it is, but I'll first describe what we knew about time and space. There's a clear inequality, right? If you run in time t, you will never use more than space t, because you will never visit so many cells or registers in your machine. So space is at most time. 50 years ago, Valiant, Paul, and Pippinger improved this a little bit. They said that if you run in time t, there's an equivalent computation that will do this in slightly less space than t over log t. This was a big result. The running time, of course, will blow up. It will be very, very expensive time-wise, but at least you can save on space a little bit. And this was believed almost 50 years to be the best you can do. In fact, we had arguments that in certain models, in certain stylized models of computation, you cannot improve that. I will not describe, this restricted model, but in some natural restricted models, you cannot beat this. And what Ryan Williams found out last year is that, in fact, much better can be done. Any computation that runs in time t can be simulated by another algorithm that uses only square root of t space. Far, far less than, before. And the algorithm is quite sophisticated and uses an earlier result of James Cook, the son of Steve Cook, of NP completeness, and Ian Mertz, that was, an essential technical ingredient. But anyway, you can, there's a really interesting way to save space, very, very non-trivial way to save space. Again, this algorithm will run in a lot of time, but at least you have a sense that, the two parameters are related in a highly non-trivial way.
Is this for a general problem? Or
general problem, and for Turing machines.
Okay.
It may not work on random access machines, or,
What's the trick? If you could explain intuitively, or is it too deep to explain?
It is, really technically explaining it, it's too deep. But I'll give you a much earlier result, which sort of indicates that really mysterious things can be done in small space. Again, it's probably over 40 years ago. People discovered the following. Well, Dave Barrington discovered the following really interesting phenomena. So suppose all you want is to count. I give you a sequence of bits, and you want to count. You say you want to know whether there are more zeros than ones, like the majority problem. Who won the vote, zeros or ones? Okay. Well, you can count, you can just add them up, and this takes logarithmic space. And it seems the best you can do. I mean, you want to count up to n to represent n takes log n bits, right? I mean, whatever n or the sum, any number between 1 and n takes log n bits. It seems essential. It turns out that there's an algorithm. I have to define exactly how it works. I will not define, I will not define exactly how it works, but it solves this problem in constant space. It seems like you can count arbitrarily high. I mean, all you need is access to whatever bit you like whenever you like. I want the 17th one, I want the 81st one, if you can have random access to the bits, even if you have constant space, you can tell whether there are more zeros than ones or ones and zeros, regardless how long the input is. The trick is that somehow you use non-commutative algebra. You use something, non-commutative algebra is not a big deal. Everybody is familiar with non-commutative things. I mean, we usually put the cart behind the horse and not in front of the horse. It matters. Or in software engineering, we do this before that. Or it's very important. The order of things matter. So you can think about applying permutations one after the other. If I rotate a circle and then take a mirror image, it will give me so these are two permutations, right? I mean, say I have n points in a circle. Can shift it by one, or I can, let's say, flip it around some diameter. There are two permutations, and they don't commute. I mean, if I first flip and then rotate, I'll get something else that if I first rotated and, think of all the points as colored by. So they don't commute. Barrington is using, he's somehow encoding the bits in the input by permutations, not large permutations of size 5. And somehow when he sees a 1, he maybe rotates, and when he sees a 0, he flips. And the non-commutativity of these operations allow him to carry out a general formula, of ands and ors and nots, any formula like this, a formula that, let's say, of some size S, it allows him to carry out this computation to really simulate the ands and ors and nots in this formula by rotations and flips of this, 5-sided pentagon. Okay? And so just to remember the configuration of this pentagon, you need, 5 bits. Right? So you need constant space. How this captures, the computation, I can tell you, one more sentence. Maybe it will not be clear to everybody, but these non-commuting things, you can do the following type of operation: do rotate, do flip, then rotate back and flip back. This is called a commutator, and it can simulate an AND gate. It's too much to describe in words without a board how it does it, but there's a very famous analogy, which is a riddle, which if nobody, I mean, it's a good riddle to think about, which really captures this end gate problem. You want to hang a painting in the following way. You have a painting, it has a string connecting the two sides, but you want to hang it not on one nail, but on two nails. Okay, there are two nails on the wall, and you can do with the string whatever you want. And the property you want is that if the two nails are there, it's hanging, everybody's happy. If you pull out one nail, doesn't matter which, the picture falls to the floor. How would you loop the string around these nails so that this happens? Clearly, this is an AND gate or an OR gate, right? And this has to do, I mean, if anybody finds a solution, they'll realize what non-commutativity I'm talking about. And it's a nice riddle. Anyway, so this type of trick where you can really, or this type of result, you can really do in small space things you wouldn't imagine possible. It's a striking example. It's really, when I heard this result, first time I was a postdoc, and somebody told me, and I just didn't believe it's possible. I mean, you cannot count arbitrarily high with a, So the trick that Cook and Mertz have in their algorithm is a solution to a natural problem in much less space than you would think. And it uses, in some sense, tricks of this nature.
So if you're counting arbitrarily large, that is information, and you're saying, like, maybe the intuition is that information's encoded in the sequence of operations.
It is encoded, yeah. Of course, you are not delivering the final count. You just say whether there are more zeros than ones. If you have to write down, of course you need, if the answer takes some number of bits long, then you need this number to write it down. If you have a decision problem, say like yes or no, like are there more zeros than ones, then you can do it for any size input in constant space. Yeah,
that's incredible.
It's pretty incredible. Yeah, and by the way, this highly applicable results used in cryptography in fundamental ways. It's used it's used in various places, and it's an extremely useful result. Here, by the way, unlike the Ryan-Williams result, if you have a formula of size S, you can do it in constant space, and the time of this algorithm does not blow up really a lot. It's just quadratic. So it's quadratic time. So this is something actually doable, useful, efficient, and and sort of magical.
We talked about the equivalence between these NP-complete problems, and then I know in practice, a lot of people, to solve the other problems, they just use SAT solvers.
Yeah.
I would have thought that would be less efficient, though, because you got to kind of translate it, and then you're doing it in almost like a different problem space.
Yeah, you usually also enlarge the instance. Usually in translation, you enlarge the instance. So what your question is, why do people use SAT solvers? I would say that there's no problem other than satisfiability that people thought so hard about really optimizing the heuristics that efficiently work on many instances. There are very, very clever ways in which you can, you are not going to guess all the n bits, but you want to start by guessing some bits that seem more pivotal, that if you, like in dominoes, maybe when you set them to one value, they force many other values to be set. And if that happens, you cut down your search space. So there are many heuristics of this type, and also more clever than this, that allow to solve satisfiability problems if they have such structure. Again, the worst case, it will not help you. There is, in fact, a conjecture this is much stronger somehow than NP-completeness, NP-complete problems taking exponential time. It says that we don't expect any savings. We expect satisfiability problems to require really 2 to some constant times n. It's not going to be 2 to the square root n or n to the log n or something like this. It's really, So but the worst case may be hard, but people optimize attacks on many such formulas that somehow have all sorts of structural properties arising maybe in practice. And I think that's the main reason that they are used. It's also convenient. I mean, it's very, people do it for testing specifications, that programs, protocols meet specification. These specifications are usually easily translated into simple constraints, and that's almost a satisfiability problem.
We talked about all the different types of resources in an algorithm, and in one of your talks, you said something where you consider randomness another resource for an algorithm. What do you mean when you say randomness is a resource for an algorithm?
In the early 70s, of course, randomized algorithms existed since antiquity, and everybody was tossing coins for lots of reasons. And of course, statisticians, do sampling and use randomness for. But when algorithmics, designing efficient algorithms became big, once we had computers, people realized that it can really enhance all sorts of computation. For example, we had no idea how to test primality of a number. And in the 70s, both Michael Rabin and 𝗀𝗵𝗵𝗀 and Strassen found probabilistic algorithms which are fast to test primality. Okay, so what does it mean, a probabilistic algorithm? It's an algorithm that's allowed to make random choices. So you can think that there's an internal, little person or device inside that tosses coins. Of course, that's not what happens. There's no little person sitting in your laptop. So the question is, where do you get these random bits? But it's very important to stress that in all these probabilistic algorithms, the underlying assumption is that the bits you get are perfect. They are half-half, each one, and independent of each other. It's like a uniform distribution on all possibilities. Now, where do you get this? I mean, where seriously do you get this? I mean, if you run a probabilistic algorithm of your laptop, since it doesn't have this person inside tossing coins, it does something. Well, high-quality randomness of this type costs money, like time and like memory. What do I mean by cost money? You can have a very cheap solution. You can just, measure the thermal noise in your computer or have one of the Intel chips. You can measure internet traffic and sample it and believe it's random. And all of these things are used. You can do something mathematical, have some simple procedure that is actually deterministic, like a linear congruence generator, something like this, and believe it's random. Or you can take the digits of pi. It also, looks random in some sense. So there are many things you can use, but you don't know they are random. If you want them to be random, one source, even this is not a perfect source, but we have quantum mechanics. People believe it works in life. It seems like a true theory of nature. There are all sorts of arguments about it, but let's put them aside. They predict that if you measure photons coming out from some source, and you measure their spin, whether it's up or down, the prediction is that each one is half-half and it's independent of each other. That's very nice, but if you are going to build this device, it's going to cost you a lot of money. And let alone that it will not be perfect, but let's leave this aside. Anyway, since you want high-quality randomness, so you have some way of guaranteeing. I mean, you're running it really on your laptop. It's not, okay, the paper was written, we can test primality with a probabilistic algorithm, now we want to run it, what do you use? So it makes sense to ask lots of questions about randomness, what guarantees the quality of the randomness, and maybe you can minimize the use of randomness. By the way, another issue with randomness is that the outcome is a random variable, and it's not always correct, right? The whole point in most of these algorithms, you just have some small probability of error. If you have a deterministic algorithm, there's no error. So you also don't like the error. So treating it as a resource is simply a convenient complexity theoretic way of saying, how do we understand, the amount of this resource we have to invest, or the number of bits we have to invest, their quality, and so on. So it's almost automatic if you think like a complexity theory. How do we minimize for particular algorithm like primality testing? Do you really need this? Do you need them to be independent? Maybe you can generate them in a, maybe you need n bits, but you can start from square root n bits or from log n bits that are truly random and make from them in some deterministic way, a sort of pseudo-random sequence, you can call it, which is a good name actually, that will, for this purpose of this algorithm, will look as if it was random. If you could do that, you don't need all these bits, you can use much fewer. And this whole theory of, reducing randomness, de-randomization, removing randomness is a huge field. And people are, there are many problems and many ways of doing it, and the story with primality is actually fascinating. So I mentioned these two algorithms that were invented, and people were wondering about the deterministic algorithm for primality. It's a problem that has been articulated already by Gauss in the most, complexity theoretic way you can, back in his days, hundreds of years ago, and maybe 150, I don't know. He was asking for an indefatigable calculator. Calculator, of course, is a person, but he wanted this to be efficient. That's basically what he was looking for, a primality test for large numbers, because they really wanted to know about numbers, maybe only a few tens of digits. They wanted to know whether they are prime or not. There was no efficient algorithm. Anyway, you can wonder about the 𝗪𝗪 or Riemann algorithm. Maybe you can use less randomness or structured randomness that you can generate from fewer bits. And nobody has any good idea. And then in the early 2000s, Agarwal, and Saxena devised a different probabilistic primality test. And it's different, so the analysis of randomness in it is different. And once you understand how randomness is used, you can maybe say, we don't need to be really totally independent bits. It's okay if it has some structure. And then they found, using number theoretic ways, a method to generate this pseudo-randomly, generate it from very few bits. And that's how so often, I don't know often, but sometimes deterministic versions of probabilistic algorithms are discovered in simply understanding the way in which the algorithm is using the randomness, understanding the analysis of the algorithm, and saying, okay, it doesn't use all that much.
You mentioned a few times the quality of the randomness.
Yeah.
How do you quantify the quality of random bits?
This is basically a question about what pseudo-randomness is, and the general answer is that it depends. You want to fool a particular algorithm, let's say for primality, so you want the randomness to fool this. You want this algorithm not to notice that you switched from perfect randomness to something that's really far less random, has far less entropy, but the analysis works nonetheless. Another algorithm, maybe you need a completely different type of pseudo-randomness for it. There's a set of examples of algorithmic problems for which when you look at the analysis, they are much simpler than this primality testing. When you look at the analysis, it seems to use not the independence of all the n bits. You really need only every pair of them to be independent, or every triple. And spaces of random variables which have this property are much smaller. You can generate them from log n bits. And so you can fool them with this. So the quality of randomness, there's a phrase I like that it's the quality of randomness is in the eye of the beholder, or in the computational power of the beholder. You really need it to be just as good as the tests that are applied to it. You just want to be completely pragmatic. You don't care whether it's random or not. You just care that an observer of a particular structure or particular computational power will not distinguish the pseudo-random distribution, which may have much less randomness in it than the perfect one.
In one of your lectures, actually, you mentioned that, and you gave a good example. And I was wondering if you could give the intuitive example of why randomness is a function of the observer's computational power.
Yeah, so if you watch this talk, you know what the example I give is the example that's taken from this fundamental paper of Manuel Blum and 𝗲𝗵𝗍𝗀. They tell you to consider 3 experiments, and the experiments go as follows. They are always between you and me. You are the observer, I am the coin tosser. I have a coin on my finger, and I toss it, and just as it leaves my finger, you are supposed to predict what the value will be when it falls on the floor, like in 2 seconds. You have to immediately say heads or tails, okay? You have to predict before it falls. Well, this is the first experiment, and what I ask and what they ask, what do you think is a success? Your success, what are your chances of predicting it? And the obvious answer is, 1/2. How can it help? What can you do? The second is when you sit there, but you have a laptop like you have now. And what can you I don't know that you can, how fast you type, but the coin will be on the floor in a second. The third experiment is where your laptop is connected to a crazy supercomputer, and the crazy supercomputer is connected to a bunch of sensors and cameras and whatever devices you want. They are all trained on my finger, okay? And so as it leaves my finger, the coin, this apparatus certainly is more than enough to calculate all the, angular momentum of the coin and the distance to the floor and the humidity in the air and whatever parameters that completely determine its motion, in particular how it will land in a split second, far less than the time needed to. So the real point in this example is that the experiment, the random coin toss, this coin toss did not change in all of them. It is masses of people in math and physics and philosophy and defined randomness in various ways. There are many definitions of randomness, and they all focus on this event, on the coin toss or sequence of coin tosses. We in complexity theory, starting from this paper, don't care about this event. I mean, the event stays the same in all. It focuses on the observer, and the only thing that changed in these 3 experiments is the computational power. So we want to know how much entropy is in the coin. If you don't have enough computational power, it seems to be full entropy. It's a half-half, right? You don't know what it will be. If you have enough computational power, you can predict it completely, and then it has 0 entropy. So what changed is the observer. So the observer is this algorithm we talked about before, and any test that's applied to, to a set of, to a distribution to test the quality of randomness. Depending on the test, you want to just make sure you want to use as little true randomness in a way that the observer will not notice. And this is the source of many of the important theorems that show that you can remove randomness or reduce randomness in probabilistic algorithms with or without assumptions, and really are behind this understanding that we have today. The randomness in algorithms is not as powerful as we thought it is. Like if you know that something like P is different than NP, or you have a hardware, traveling salesman is exponentially hard, or 𝗧𝗵𝗵𝗀𝘀𝘁. If you know that, then in fact, I can give you a pseudo-random generator that will de-randomize any probabilistic algorithms. We know that under this assumption, we have what we call P equals BPP. Anything that has an efficient probabilistic algorithm also has an efficient deterministic algorithm. You just need to know that there is a hard function somewhere. Under what assumptions do we know P equals BPP? The assumption, very natural, is that one of these NP-hard problems, or in fact even problems in higher classes, requires a lot of hardware, require exponential size circuits to solve. Okay, we believe that. It's like P versus NP is strengthened. You cannot cut down the exponential search space. So maybe people are happier with this assumption, but this assumption about time complexity, it has no randomness in it. It's sort of, at first it's shocking that it's actually related to the problem of removing randomness from algorithms. So that's one fundamental connection. It's this hardness versus randomness paradigm. But we know even more. We know that it goes both ways. We know that if you are trying to remove randomness for some algorithms, if you can do that, then you found the hard function. So there's really it's not an exact if and only if, but again, and there are many variants of this. In some variants, it's if and only if is stronger. But we really know that it's really one of the other. And since it's hard to believe that all these hard problems are easy, or the seemingly hard problems like P equals NP, we tend much more to believe the other alternative, namely that randomness in algorithms is weak and you can remove it.
OpenAI, Anthropic, Cursor, and Vercel all use this product to make their lives better. And the problem it solves is when you're building SaaS or an AI product and you want to sell to other companies, there's all these requirements you need to meet. There's SSO, there's SCIM, there's RBAC, there's audit logs. These are all things that take time to integrate, but aren't the main focus of your app. WorkOS is an API layer that lets you meet all of these requirements in just a few lines of code. So let's say you have a new SaaS product and you want to sell to other companies. WorkOS will solve all of these critical feature gaps for you. You can check them out at workos.com to learn more and get started. And I appreciate them for supporting my work and sponsoring this podcast. Is there an intuitive explanation for the relationship between problem hardness and randomness?
Yeah. There's almost always an intuitive explanation for. So what's a hard problem? I give you the input. You are a limited computer. You are a polynomial time algorithm. I give you the input. Let's say it's a traveling salesman problem, or you don't know the answer. So there's some entropy in the answer, right? It's in the same sense we discussed before. There's some entropy, a tiny entropy, maybe exponentially small entropy, because maybe if the input is random, maybe only few instances are hard, and all the others you can solve. But at least you see a hint of a relationship between hardness and entropy. This, of course, is not satisfactory because we want that for you the answer will be like a coin toss, not like a very biased coin toss. So we need to find ways to amplify this uncertainty for you. Amplify the hardness. We want not just that some instances will be hard, but that the random instance whether the answer is yes or no for a polynomial time observer will be half-half. It will not be able to gain an epsilon advantage over a random guess. So for this, we developed all sorts of methods that amplify randomness. Now, this doesn't solve the problem at all because I managed to take n bits, a random instance of a problem, and manufacture one bit that's hard for you to guess. Well, I could have taken the first random bit I picked for the... So I generate from many a few, one. What you want to do is the opposite. You want a method that will take a few and will generate many. Right? That's a pseudo-random generator. Pseudo-random generator starts with a few truly random bits and generates many. And for this, we need other tools. There's something that I developed with Noam Nissan, called today the NW generator. I like to say that, people say that making the first $1 million is easy, and afterwards you can make many more millions. You can think of it this way. The hardness, in the way I describe it, allows you to make $1 million. But once you can make one, there are methods to make many more. And in fact, more than the number of bits you started with. But still, their quality depends on the hardness of the function you use. We still use this, and your limitation of being running polynomial time. So you cannot solve this hard instance. You build many, many instances from a short seed. You start from maybe a logarithmically long seed. You take many subsets of this, like n, you will need n of them. And I ask you for the value of the solution to each one. Each one is hard, but you want to say that they are simultaneously hard. You cannot tell them apart. There is no correlation you can detect between them, even though they are extremely correlated. So we have methods to do that as well. So that's the connection. You embed having a hard problem to a limited observer means there's some uncertainty about the answer. That's a key. That's a starting point.
So when you say that the quality of the randomness is a function of the computational power of the observer, one thought that comes to mind is, imagine I have maybe infinite compute, then nothing is truly random. Is that accurate to say? Like, if I had infinite compute, the weather is not random. Yeah. Nothing is random.
Okay, so it points to the fact that you have to really be careful about what question you are asking about the randomness. If you want, to apply this to probabilistic algorithms, then it's really important that you are limited computationally. So if you have infinite compute times, you will be able to distinguish a distribution with full entropy, truly random, and one with coming from a generator, one with low entropy. So you could do that. But one thing you cannot do with infinite compute is something that's information theoretic. So there are many other things we need to do with random bits than just run probabilistic algorithms. For example, we want to generate passwords for our, crypto, for security systems. There, the very demand is that they are random, right? I mean, Shannon's theorem tells you, the quality of your password is as good as the entropy in it. So the notion of a secret rests on the randomness, the true randomness of the... So if I just ask you to produce a random bit, or you ask me to produce a random bit, whether you have infinite computational power or not, doesn't matter. I mean, to generate this random bit, it has to be random. I mean, your demand is not that it will succeed in some test. You really want the probability of heads to be half, tails to be half. This, then this definition or this task of producing randomness is not related to your computational power. So, lucky or unlucky, I don't know, for us, many times we do have implicit or explicit tests for this randomness. You say, I can break this, I can break this system or something, and then you can maybe use pseudo-randomness. But if your very demand is to have a random event, then you need to produce a random event.
I saw when I was doing my research that there are ways to create higher quality randomness by aggregating weaker sources.
Yeah.
How does that work?
Well, it's another theory. I talked before about the theory of pseudo-randomness. There's a whole different theory. They are related in non-trivial ways, but it's called the theory of randomness extraction, or randomness purification, maybe. And this is exactly what you asked about. We imagine that the world maybe does not give us perfect randomness, but we have all these events we cannot predict, like the weather, or various quantum phenomena, or sunspots, or we cannot predict the, stock prices, right? Otherwise, the market will be. But these are not, even though these are unpredictable events, they are somewhat predictable. I mean, the weather tomorrow is more likely to be similar to the weather today than the opposite of the weather. So there are correlations. If you sample this weather, for example, there are also biases. I mean, sometimes in the spring it's more, or in the summer it's more likely to be hot than cold. So there are biases, correlations. These are called weak random sources, and there is a mathematical quantification of how weak they are. Basically, talk about the amount of entropy in them. You have n bits, potentially you can have entropy n, but maybe they were generated from a generator or they came from some source of, we don't. So it has some entropy in it, but you have no idea where. I mean, maybe half of them are fixed and half of them are coin tosses, and you don't know which half. Maybe they are each, half, 3/4 0 and 1/4, heads or tails have a bias that also has lots of entropy, but not full. And maybe the correlations are even more complicated. So you can imagine all sorts of situations like this, and you mathematically model it by saying, okay, there are n bits, it's a probability distribution on n bits, which has some entropy, let's say square root of n. You don't know where. And you want to use it in a probabilistic algorithm. So it's a basic question. Can we use physical events, weak sources coming from nature maybe, in probabilistic algorithms? And it's certainly not obvious. I mean, just feeding them to the algorithm as is not going to work. They are very easy to find simple algorithms that will fail, that will succeed on perfect randomness and will fail on, will always make an error, let's say. But the theory of randomness purification wants to take this sample of n bits with some amount of entropy which is not full, and somehow massage it, create from it maybe a shorter string, which is of higher quality. Ideally, it will be perfect random bits. So ideally, you can imagine that if I have n random bits and I have entropy root n, maybe I can massage out of there square root n, or maybe just the fourth root of n, bits that will be essentially uniformly distributed. Then if I have an algorithm that just needs this amount, that's what I feed it. It turns out that you cannot do that. It's impossible. But what you can do is not produce one string of length, let's say square root n, but you can produce n to the 100 of them. Okay? And what you are guaranteed, so this is this randomness purification device. There's an efficient algorithm that takes any distribution with entropy in it, and you produce many blocks, polynomially many blocks, of the length roughly the entropy, what you would hope to be perfect, and what you are guaranteed is that 99% of them are truly perfect. So you have many, 99% of them are as good as perfect, and there's 1% which is bad. You don't know which it is. But that already solves your problem, because run your algorithm on each one of them, take a majority vote. Doing this is extremely complicated. There are many ways of doing it. There are variants of various assumptions you can make about the entropy. Maybe you have several weak sources that are not related to each other. There are various, the various variants, and this theory is very well developed. But we know that the statement I made essentially is accurate. If you have one source with some entropy in it, you can generate polynomially many samples of the length of almost the entropy, and most of them will be perfect. So that's as useful as having one, yeah.
I vaguely remember skimming a bunch of papers, and one of the papers I had this figure where it was a two-dimensional array of numbers, and I think they were like drawing rectangles or something like that. Is that like one of the ideas?
So it's a notion of pseudo-randomness, which is related to one particular variant of this extraction problem, where you have several weak sources, not one. One is the hardest, because that's, yeah. But maybe you have a few that are independent, and each of them has some entropy in it. And I think what you are referring to is this sum product theorem, this I cannot draw the pictures of there, but you don't really need to. So let's just think about this problem. You have three sources of randomness. They are each weak, so each has just a little bit of entropy in it. And all you want to produce is one source with somewhat larger entropy. So you are losing in the number of sources, but you are gaining entropy. If you can repeat it, you eventually get to full entropy. So that's the idea. So what combination of weak sources would you take? It's not obvious. And the solution, this is certainly there is, maybe you mean this one. There's a paper I have with Barak and 𝗵𝗵 about this particular problem, and we are using a result in what's called the arithmetic combinatorics, and I can explain it very simply. I think that we learn about addition in second grade and about multiplication in third grade maybe, and the only motivation for multiplication is that it's a way to shortcut repeated addition. And that's all we talk about. Then if you go to college, you learn that, sum and products are the basic operations of fields. You can do it with integers, you can do it with rational numbers, complex numbers, finite fields, and so on. So you remember, these are the basic operations. But how do they relate to each other? It's not clear. It's not. Maybe there are many ways to ask this question. But one way to ask this question that was suggested by 𝗪𝗪 and was solved the first time by 𝗪𝗪 and 𝗬𝗵𝗪𝗍, and then in a much more, in the form we really need by 𝗪𝗵𝗲𝗀𝗀 and 𝗪, say the following. Just think of a set of integers and add all pairs. So you start with, let's say, k integers, add all pairs. How many new integers do you get? This you should think of as entropy increase. If you get many more, somehow, So you have k integers. Well, it depends what they are. I mean, if they are the first k integers and you add all pairs up, you get just a number between 1 and 2k. That's not much larger. That's a factor of 2 larger. If you want to increase an entropy, you want to get, some power of k bigger than 1. Of course, if you take a random set of integers, you'll get k squared. They will all be distinct. You get k squared integers. So somehow you want to say, it would be great if for any set when you take all pairs, you grew. But it's not true by this example of the interval. Well, you can not take sums, you can take products. Okay, but also products don't always increase. If you take, 1, 2, 4, 8, you take a geometric progression, you multiply all pairs, you just get just twice as many as you started from. So that's also not good. And the magic in this sum product theorem is that sums and products are orthogonal to each other. Somehow, if one of them fails to grow a set, then the other will grow this set. And so this is an amazing result. And the way you use it in this context, you think of the outcome of your sources as numbers. You, let's say, multiply the first pair and add them to the third. You mix the sum and product. So this guarantees, even this is not obvious, but if you do this, it guarantees that you grow the number of different values you get is significantly more than k, maybe it's k to the 1.5 or something. Entropy does increase, and that's the source of, you need to prove it distributionally, it's not just a size, the entropy is not just size, log the size, it's more than that. But anyway, this is behind one solution to one of the problems about purification. It does not solve the one source problem. This you need other tools.
I saw that you had done some work in zero knowledge proofs. I was wondering if you could explain, what is a zero knowledge proof, and maybe we talk about its significance.
Sure, yeah. Zero knowledge proof, it's pretty amazing that it became a household word. I mean, it was in the domain of theorists for a long time. The original definition of zero knowledge proof came in a seminal paper of 𝗀𝗫𝗀𝘀, Micali, and Rakov, which also contains the definition of interactive proof. So even before zero knowledge, they conceived of the notion that proofs don't have to be written down like in mathematical papers. People can have a discussion, a randomized discussion in which I try to convince you of something. Or I want to prove to you something, like I know the proof of the Riemann hypothesis, or I can solve this Sudoku puzzle. And we can do it interactively with the we are randomized, in particular you, the verifier of my claim, are allowed to be randomized. So it's like in randomized algorithms, but now the prover, there's a prover, it's not just an algorithm, there's a prover like in NP, someone who knows the solution. But the convincing has this interactive form. So this model was suggested in this paper, and also in a paper of 𝗵𝗵, parallel in the same time from different motivations. Basically, it offers a generalization of the notion of NP. NP is just when I send you a message and it convinces you, you verify it and it convinces you. Now we allow an interaction, and we allow a small chance, because you are randomized, we allow a small chance that you will, I will convince you of a false claim. But this error can be reduced, like in probabilistic algorithms, can be reduced arbitrarily. You want 1 in a billion, you can get 1 in a billion, whatever. Yeah, anyway, so there's a notion of an interactive proof. And then in the 𝗀𝗫𝗀𝘀, Micali, Rakov papers, they suggested another notion of interactive proof, which is more restricted. You want to prove something, but the zero knowledge means that you want the verifier to learn nothing, absolutely nothing about the proof, except that it's true. Now, this sounds really totally ridiculous. I mean, if you think about the last time you convinced somebody to change their mind about anything without providing them any knowledge, any new things they didn't know. Say, what are you talking about? Such proofs don't exist for anything. There's no zero knowledge for anything. They were not thinking about, convincing someone of, political opinion. They were thinking about cryptography, of course. They've created the foundation of cryptography in many other papers. But they are imagining cryptographic protocols in which you have secrets, and you use these secrets in your computation, and you have, the protocol tells you to do things that if you don't, then, you're violating the protocol. So the others don't want you to cheat. They want to make sure you perform the right operations on your secrets. For example, you are supposed to pick a public key by multiplying two prime numbers. If you multiply 3 or something else, then you are violating the protocol, and maybe security is not guaranteed. So I would like to convince you that the number I give you is actually a product of 2 primes. I certainly don't want to give you the 2 primes. So what I really want to convince you of is that I computed this number by multiplying 2 primes. And you learn from this interaction absolutely nothing except you are convinced with very high probability that I did multiply 2 primes and not any other number, and I didn't do anything else that I shouldn't have. And you can think about lots of other cryptographic protocols where people are doing things like multi-party computation, very complex things. They are computing with their secrets, and they don't want to reveal them, whereas the others want to make sure that they did what they should. So there's any number of applications to this idea. The only problem is that it sounds ridiculous because it sounds impossible. In mathematics terms, if somebody came here and said that P, they proved P different than NP, I would want to see the proof, and then tell me, okay, I'll prove it to you in 0. Now, how can anybody convince me that they have a proof of P different than NP, and I come out, congratulating them and, amazed by them, and nevertheless, I know absolutely nothing about the way they proved it. I just know that they did. So it really sounds ridiculous. And certainly one of my favorite papers, maybe my favorite, is the zero-knowledge paper, which came a year later. It's joined with 𝗪𝗲𝗀𝗀 and 𝗂𝗵𝗪𝗀𝗀, where we showed that it's not only not ridiculous, it's universal. Namely, anything which has a proof, a mathematical proof, also has a zero-knowledge interactive proof. Anything, like P different than NP, or that I multiply 2 primes, or anything that you can prove revealing your secrets, you can prove without revealing your secrets, and convince beyond any reasonable doubt. So that's possible.
What's the intuition behind that? Like, let's say I have a proof for P equals NP, and we want to convert it to a zero-knowledge proof. How does that work?
How does this work? Well, first of all, it assumes cryptography. So we assume we have some one-way functions. We assume that some, problem like factor integers or discrete logarithm or any number of believed one-way functions exist. So one-way functions, if people don't know, are functions that are easy to compute in one way but are hard to invert. For example, multiplying numbers is easy. Finally, the factors of a number, which is the inverse problem, the prime factor, is believed to be hard. Of course, we can never, we don't know any hard problem. That's the P versus NP question. We don't know. But we believe about many problems, and the belief is actually the whole world believe, because the whole world is using cryptographic systems which rest on this. All electronic commerce assumes this. So we assume this. So assume we have one-way functions. One-way functions allow you to create basically garbled message commitments. I can, I have a number in my head. I don't want to tell you what the number is. The number is between 1 and 100. I can write down another number, which looks like a random number to you. And on the one hand, you have no idea. I claim this encodes my secret, okay? And this commitment scheme, which is built very simply from one-way functions, guarantees two properties. A, you cannot tell what is my secret, even though you can see this number, this other number I gave you. And on the other hand, I cannot change my mind about my secret. It really commits me to so I can later provide you with a certificate that I was thinking about 17. And I can only do it for 17. I cannot do it for any other number. Okay? In fact, a very simple example is really using factoring. In some sense, the product of two primes, this number, it's easy. This number commits it to its factors. It uniquely defines its factors, right? The only problem with this is not exactly random products of primes. It's not. Yeah, but you can do it, so you can do this. Okay, so now that we have to take commitments are possible. That's very important. So I'm describing very high level. I'm hiding lots of things, and even the definition of zero knowledge, the formal definition, is quite intricate. It's not, the intuition is obvious, and I said it, but actually formally defining it is not trivial. But at a high level, I'll give you some idea about how a zero knowledge proof looks like. Now we have to think about what theorems am I proving to you. And it was very important to us to figure out what problem to think about, even though today you can do it for others, but we were thinking about theorems of the type, here's the graph, we can color it in 3 colors. It's also a formal mathematical statement, either it's doable or not, right? And we simply focus on proving in zero knowledge claims of this type, okay? The graph, we both know, I claim I can color it with 3 colors. You don't believe me, you want to be convinced of this fact. And you don't want me to cheat you, you don't want me to be able to, it should be an interactive proof. And moreover, I want it to be zero knowledge. I don't want you to have a slightest idea of what my coloring is, or what anything you didn't know before is. Okay, so roughly the way it works, zero knowledge proof for this particular set of claims, that are certainly not all claims, they are very structured claims, will look like the following. We iteratively repeat the following procedure. I put commitments for the coloring on every vertex. I tell you, I don't tell you it's green, red, or blue, but I put a commitment to one of them on each vertex. You will choose at random an edge of the graph and ask me to open these 2 envelopes, to decommit. And you will check that the colors you see, first of all, are in this set. They are not gray or orange. They are either red, green, or blue, and that they are different. This should give you some, maybe slight, slight advantage or slight support to the belief that maybe I'm not cheating you. Of course, it's a very limited one because I can cheat you in some corner, yeah. So we have to establish 2 things. We will repeat this again and again. We have to establish that it's it's a proof, it's an interactive proof, that I cannot cheat you, and we have to argue the zero knowledge part. Okay, so let's do one at a time. To do the correctness that I cannot fool you is very simple, it's the following. If the graph is not 3-colorable, whatever I commit for, there is one place which is an error. Either it has the wrong color and not allowed color, or 2 colors are equal. You have some non-trivial chance of catching this with your random guess, right? I mean, it's 1 over the number of edges. It's not so small. It's a graph with 100 edges, it's 1 in 100. If thousands, if we repeat it not 1,000 but 10,000 times, the probability that you don't catch me in any of them drops exponentially to 0. Right, so of course, so this establishes that I cannot fool you. The zero knowledge is a more serious problem because if I keep using the same coloring, you will ask me about this edge, and then eventually you'll know the coloring of all colors. Here's something that's really special to the coloring that is being used. If I have one coloring of the graph, I really have 6, because I can permute the names there. I can replace red and green, and it's another valid coloring. So what I do really in each one of these iterations is not using the same coloring, but using a random one of these possible 6. They are legal, they are all legal, and I just use one of these 6. What's the advantage of this? When you open a pair of vertices under this distribution, one of the 6, what you will see, if I do have a coloring, and that's the only, I want to stress, we only have to establish zero knowledge if I really can prove the theorem. So if I do know the solution, the proof, I want to protect my knowledge. What happens when I reveal to you 2 of these colors on the adjacent vertices of the graph? It will be true. In this distribution, when you restrict it to 2 vertices, it will simply be 2 different random colors, right? This is what you get by all permutations, these 6 permutations. What did you learn from this? Nothing. You could have picked 2 random different colors. You didn't need me for that. So you didn't learn anything. So in each iteration, you learn nothing. So this is the idea of the proof. Well, this is the end of the proof that I can, that showing that there are zero knowledge proofs for all graph coloring, 3 coloring problems. What about all the Riemann hypothesis and the p-verse NP and factoring and all these other things I want to claim to you and prove with zero knowledge? Here is very simple. You use NP completeness. This is an NP complete problem. Anything that can be proved is really something in NP, right? This is the definition. So you reduce it to 3 coloring, prove it in zero knowledge. And the main point about reductions in NP is that they don't only convert the yes-no answer in a consistent way, that if this is solvable, this is solvable. But actually, if you have a witness, if you have a proof for, I don't know, whatever, it will become a legal 3 coloring of the graph you generate. So if you have a proof, you can also have the 3 coloring. It's very important that the reduction also provides a translation not just between the instances, but also between the proofs. So NP completeness theory gives you for free that if you solve the problem for graph coloring instances, you solve it for you can prove anything in zero knowledge.
So with the zero knowledge proofs, you can never be 100% sure.
No.
Okay, but practically, I mean, exponentially approaching.
You can make the completeness 100%. Namely, if I do have a proof, you will be there will be no error in your. But there is a slight possibility that the graph is not 3 colorable, and you will not catch me. You can make this exponentially small. You cannot make it 0.
When I think of cryptography, one-way functions, there's this idea of quantum computation that's kind of changed complexity theory a bit. And
big time, yeah.
Yeah, and I wanted to ask your thoughts on how quantum computation, or that model of computation, is changing complexity theory. Like, what are the big takeaways?
Okay, let me say what it is, first of all. I mean, quantum mechanics is a theory of nature that, seems to be, everybody believes and accepts. So, like with randomness, we can ask why not enhance computers with, this physical knowledge. We allow our computers to operate in the, way that quantum mechanics dictates, namely manipulate bits in superposition using unitary operations, whatever this means, but according to the rules of quantum mechanics. And really strange things happen in quantum mechanics. I'm sure many people know, because you can there are all these interference patterns. It seems that you can. Basically, you are working with probability theory with negative numbers. Events cannot, aggregate only. They can cancel each other. And, okay, so it's a model of computation. It's a generalization of Turing machines. In fact, it's a generalization of randomized Turing machine. It's very easy to see that a quantum computer is at least as strong as a probabilistic computer. How do you see it? You just measure the quantum bits before you start. You measure them. This is what I mentioned about the photons in the beginning. If you have some basic superposition on, a quantum bit, if you measure it, you get a random bit. So because of that, quantum computers are at least as strong as probabilistic computers. Okay, so it's a model of computation, and it was suggested in the 80s. Feynman and Manin and others suggested, letting algorithms use these quantum mechanical operations, mainly originally for just simulating quantum systems, rather than building big apparatus like we simulate other things, turbulence, I don't know. What's the power of quantum algorithms? Again, let's say running in polynomial time or efficient quantum algorithm. Can they do more than efficient classical ones, deterministic or probabilistic? And it wasn't clear for a while, and there were a few examples that were very stylized, but were not for concrete natural problems we care about. And then in 1994, Peter Shaw sort of, created an earthquake or an avalanche. He found quantum algorithms that are efficient, that factor integers, and also compute discrete logarithms, the two most basic underpinnings of all security systems that exist. And this set the world on fire, right? So lots of people try to do a lot of things. Of course, people want to have them, these algorithms implemented. Maybe they want to break or other people's crypto system. So, as you know, since then, billions were invested by companies, by governments, by lots of people trying to build the technological infrastructure. And this is extremely complicated. Holding bits in superposition is extremely complicated. There's things that are called the noise. When people build classical computers, like von Neumann here in the building next door, noise was one of the serious problems because the bits were really in vacuum tubes. And they had to contend, and in fact he built a nice theory of classical computers that have errors, noise, that have to cope with errors. Some of their components can be faulty. But today's hardware, has no errors to speak of. There are error correcting mechanisms, but we don't need them for classical computing. Intel chips don't have, I think, error correction in them. Hardware is very reliable. When you move to quantum, there is this decoherence noise. In quantum mechanics, everything depends on everything. The world can influence the computation in your laptop. And protecting from this is very hard. There are quantum error correcting codes, and that's part of the solution. That's only one of the problems. Just holding bits in superposition is hard, and there are many hard technological issues, and there's progress on that. So this is one line of huge investment. The other line comes from cryptography because, of course, everybody should be worried, right? Forget quantum computers. If tomorrow, really tomorrow, somebody finds even a classical factoring algorithm in polynomial time, I think there'll be chaos in the world because nobody can do any transactions because most security systems still rely on factoring. And so, of course, we want to change the underlying assumptions of security. we want to rely. The whole revolution in cryptography was that we rest cryptography on computationally hard assumptions. And with this, we build all the wonderful public key systems and, all the magical things you can do with by assuming that players are computationally limited. But now, if the adversaries are quantum computers, then suddenly they can break this assumption. You want to find other mathematical problems, computational problems, which are somehow hard even to quantum computers. So that's the whole field. This changed complexity theory and cryptography. There is an army of people who are just trying to invent problems. I maybe should stress, one-way functions are easy to find. I mean, most processes in nature are not easily reversible. You make an omelette from an egg, reversing this is, doesn't take the same amount of time. That's the usual example of a physical one-way function. But trapdoor functions like factoring, problems from which you can build public key systems, and that's the most really basic thing for electronic commerce, are few. We don't know many, so we know this. I mentioned factoring discrete log. In the 90s, 𝗫𝗫 and dwork created this another type of trapdoor function from problems on lattices in high dimensions. I will not describe it, but it's another problem, and then people refined and got a few more similar nature. And it turned out when Peter Shor discovered this, people immediately tried to solve other problems with quantum computers. In fact, even today we cannot solve too many other problems with quantum computers. These are special. The special thing about them is that somehow you can reduce them to finding periods in a signal, and periods is like Fourier transform. A Fourier transform turns out to in exponential space, but Fourier transform you can do somehow with quantum computers, with interference. The lattice problems and problems related to it, some called learning with errors and similar, to this day, nobody found an efficient quantum algorithm for them. So there's no even theory. Forget building quantum computers. We don't know how to solve them. And so what the world is not just complexity theory, the whole physical world of, security systems, and also governments like the NSA, is, supporting or, asking the world to produce assumptions that may be resilient to quantum attacks. And so this is a huge change. There is a major change in the interaction between computer scientists and physicists, which grew tremendously since this discovery. And it's rich in many, many ways that are not... the influence of the algorithmic thinking on physical theories, including today theories in quantum gravity, black holes, and so on, is immense. And we have new sources of problems and new models and new complexity classes, etc., etc. And there's a fantastic interaction. And it's also enriched complexity theory in that it turns out that you can discover quantum algorithms and maybe then dequantize them in special cases, like I mentioned factoring before, the randomizing. And so sometimes it's a road to discover new algorithms. It reveals connections between problems. It's extremely rich. But one of the maybe most amazing consequences is that people, we, being what we are, we make up models and study them. And the interactive proofs I mentioned before, turns out that even before quantum, they were generalized to interactive proofs not with one prover, but with many provers, which seem to be, weird, but turns out to be very important in itself because it led to the 𝗶𝗶 theorem. then people said, okay, let's allow quantum verifiers, quantum provers, and see what they can. So one amazing result, which is about 5 years ago, is the acronyms. Of course, we have acronyms for all these complexity classes. It's MIP star equal RE. You may have seen it, maybe you didn't, and it looks weird, but I'll tell you what it says really. It says that there is a weird, really weird proof system with quantum provers that trying to convince verifiers, an efficient verifier. And it turns out, you ask for which problems can they do it, forget their own knowledge, just convince. And it turns out they can do it for the halting problem, for problems that are not computable. Things that are not computable are verifiable by efficient verifiers if the provers are quantum and they are entangled and whatever. But it's a weird proof system, very weird, but it does something that looks totally, ridiculous. Things that are uncomputable by any classical computer are verifiable in this interactive probabilistic sense by efficient verifier. So what I like to say in talking about this is that it seems that the best hypothetical reaction of anybody who hears this, okay, you complexity theorists, you play in your sandbox and you build all these sandcastles and make up all these models that have nothing to do with anything just because you can, and you get, once you weird enough, you get weird enough, consequences. So one message, which I think is very powerful, is that this result has absolutely fundamental impact on math and physics. It turns out that it implies, and this was already done in the initial paper, it implies resolution of well-known conjectures in math and physics. It turns out that, weird as it is, it's a new mathematical technique to solve problems that nobody had any idea, famous problems, important problems that fields were dedicated to, are resolved by this result, by the techniques of this result. So you ask the impact of quantum. You see, the impact is many generations over for different motivations and developments, but all of them following the methodology of complexity theory, of understanding the power of computational models, proof systems, and so on, has magically led to such a consequence. And this is just, we are in the beginning of this, right? This type of proof technique is now being explored and used, and there are more results, using this type of techniques to long-standing problems. Pretty amazing.
That's incredible, yeah. I mean, in complexity theory, there's these, what do you call them? I guess like Venn diagrams of all possible problems. And, the implicit assumption in this picture is that these are decidable problems.
Yeah.
In some of these diagrams, there's a little, in the corner, there's a undecidable ones. And,
unreachable, yeah.
Right. And it's just, I can't, I don't even understand how you could verify an undecidable.
It's a 200-page paper. It builds on 10 years of understanding, which is both a lot of development in the quantum algorithms and quantum proof systems sphere, but also relying on techniques from classical proof systems, which have to do with coding theory and various algebraic stuff that is used to prove, for example, the PCP theorem that I mentioned. It's, it's a huge body of work, and on top of this, they wrote this 200-page paper in which they had to develop many more tools. And there you have it.
Wow. I mean, when someone produces 200 pages of such complicated work that makes such a outrageous claim, how does that get verified by people?
Yeah, it's a very good question. This tool for any mathematical result that is complicated, and of course you know that of course proofs of 𝗵𝗶, NP, and the Riemann hypothesis are generated very frequently, but some of them were generated by very serious people and took a long time to refute in these two cases. But others, like the Perlman proof of the Poincare conjecture, one of the Clay millennium problem, $1 million problems, was another one like that, and this took several years to verify and fix small bugs in, and books expositing this proof were written, and eventually this particular paper is for some reason still in the refereeing stages in the Annals of Mathematics, now probably almost 6 years. It will be done. It's robust in the sense that already new papers were written with this type of tools, in fact giving somewhat alternative proofs of the same statement and stronger statements in order to resolve other mathematical conjectures. But yeah, it's a serious thing, and in fact the original paper had a bug, like the original paper with Fermat by Wiles, Fermat's last theorem, also had a bug, and it was fixed. And this was fixed. This was very early on, just when it came out very quickly fixed. So it's any mathematical claim. Your question is very important for. In general, mathematics and mathematical truth is a social construct. It's what mathematicians believe. Maybe we are moving into a world in which we have lean proofs of, we have a formal way of writing proofs, and you can maybe formally verify them. But anyway, I think that this community is quite certain about, yeah.
In complexity theory, it's very mathematical in nature when I read the papers, but obviously it has implications in computer science. What's the relationship between math and computer science to you?
Well, I think the theory of computer science, my field, complexity theory, algorithms, this theoretical side, is really lucky to have these two parents. It lives in both spaces. It is a mathematical field in the sense that most of what we generate are theorems and proofs in the mathematics sense. On the other hand, it's related to computation because the kind of questions we ask ourselves, the problems we are trying to solve, are motivated, partly motivated by trying to understand computation. So you can think of theoretical computer science very much like you can think about analysis and algebra and topology. There are notions, in algebra you are trying to understand equations or systems of equations. And in analysis, you are trying to understand, very generally speaking, inequalities and continuous spaces, right? So there are these notions you are trying to understand. Computation is one of these notions. You are trying to understand what can you produce by an evolution of simple local steps to a given environment, the input, and this can be a sequence of bits, or it can be the DNA of a person, which is being, from which you produce proteins using computation, or you produce a new baby using the evolution of, a fertilized egg, or the weather, or, so computation is sort of everywhere. And we are trying to understand it in ways that are different, right? We care about resources, how much resources are exerted in any such computation, and trying to model it, try to understand the algorithms that underlie natural phenomena. So we live in both spaces. We have a lot of input of problems and models from, industry, technology, systems, and so on. And we have all the mathematics that is, so we have the rigorous side coming from, and the aesthetic side, I would say, like creating models of proof systems because they are nice, because they are interesting, because, not because they are implementable necessarily. So this living in these two spaces, is extremely beneficial to this theory of computation.
You mentioned earlier that some people might have the perspective of complexity theory that it's kind of solving problems for problem's sake. I read in another interview you did that you were never motivated by application. And then my natural thought was, what motivates you to solve all these really tricky, complicated problems?
Okay, so let me say one thing about the beginning of your question. It says about solving problems. I think that what we do much more, is modeling things. I mean, modeling things then give rise to problems that you want to understand. So I think the modeling part in the theory of computation, modeling various forms of computation, is a large part of theoretical computer science. Manifests itself in particular in cryptography, where there are models of adversary in distributed computation. There are many. I think modeling, just asking questions, is and creating, making definitions, is a very central part of the field, and it happens more than in mathematics, maybe because they are more ancient and maybe definitions happened earlier. But I want to stress this. That's a very important thing. For example, we discussed randomness, and our definition of randomness is totally different, and it gives rise to very surprising and interesting practically theorems. Okay, now that we settled that, what motivates me or what motivates other people? Of course, everybody has their own motivation. I am a product of computer science education. All my undergrad and grad school and postdoc and everything were in computer science. So I think that I certainly am sorry that I didn't take many more math courses, because then I wouldn't have to learn things later in life. But that aside, I think that the focus on computation, which is what computer science education gives you, different systems and different issues. There are, of course, algorithms in databases and algorithms in programming languages, and in fact famous algorithms. In other fields, there are models and algorithms. And so computation is something that I'm interested in intrinsically. I'm more over the years realizing that computation, the field expanded to interact with all the sciences, and that computation happened everywhere in various forms, in physics and biology and so on. Makes it a fundamental object of study. And for me, given the way I was brought up, I guess, particularly, is fascinating in itself. I know from just experience that lots of the theorems we prove, not many, but probably with much higher proportion than in other areas of math, are impactful in the world, in real systems, in security systems, in blockchains, in the real world. But this particular side of seeing exactly how you translate your algorithm into a system, or your zero knowledge proof. I predicted when we came up with the zero knowledge proof that it will never be implemented, because the protocol that I described more or less to you is very costly. I mean, you want to prove that I'm producing a product of two primes, and I convert it to a map, and then I do all this complicated procedure many times. So it doesn't seem that anybody would ever use such a thing. But I was wrong. I mean, I didn't realize how motivated people can be and how important applications of zero knowledge can be in the real world, not in theory of protocol design. And they did simplify, maybe using more assumptions, different assumptions. There's a recent breakthrough of a postdoc here, 𝗲𝗚𝗚, you may have heard because it got some publicity in Quanta and so on, where he introduced into the assumptions of cryptography not just hard computational problems, but also things of the nature of Gödel's theorem, that something is unprovable in some mathematical proof system like 𝗬𝗵𝗻, whatever mathematicians use. Somehow using that, they can get zero knowledge that's non-interactive. You can get, it's an amazing thing. It gets, things get richer. What I want to say is that, again, from experience, I have 45 years of experience of this working in this field, which have been fascinating. I mentioned to you in the email, there's extra benefits to this field. I think the community is amazing, not just that it has so many brilliant minds, and young, brilliant minds are entering the field all the time, but it's also very lively and interactive and collaborative and, many of my best friends are also colleagues, so it's fantastic. But the understanding that, the theoretical understanding of many things that we maybe ask ourselves for aesthetical reasons that are mathematical, that we generalize something for generalization's sake, which may not have a counterpart in industry. In fact, Shor's work on quantum algorithms, you can say, why do that? There are no quantum computers. Maybe let's wait till somebody builds one and we understand why, So no, the answer is no. No, you should try to understand whatever is natural for you to understand. This field has already, maybe it was not clear 40 years ago, but certainly clear now, that lots of theoretical understanding is not just productions of mathematical results, but because it is about computation, it is meaningful, often enough or whatever in the real world. And there are many, many other examples besides crypto and quantum. In coding theory and, the field revolutionized coding theory mainly because of the PCP theorem, tools needed for. There are lots of examples, and this eventually went into systems, for memory schemes or whatever. Look, I'm interested in P versus NP. This is a question about impossibility, right? This is a problem. We still didn't get closer in this, at least certainly the years I've been at it. We are not much closer to showing hardness for anything. We don't know that multiplication is harder than addition. It's a basic question. This kind of question by itself is certainly not practical. I mean, it's not clear. Well, it is a little clear, because if you find out functions, maybe you can substantiate cryptography on a theorem rather than on assumption. But anyway, there are questions in the field that don't directly relate and will not directly relate to implementations of any system. But they are all part of trying to understand what efficient computation can do and what it cannot, or when can you minimize resources of some type, and when you cannot, and how do different problems relate to each other. This basic methodology of the field that created some wonderful edifice. And I would say that we are still in the embryo stage of understanding computation.
You mentioned a few times in this conversation, some people made a major discovery and then it, kind of broke some assumption that was maybe 50 years ago. And, researchers make these advances. And I know in your career, you've made a few as well. And the time space between payouts is sometimes decades, where you make a major.
Yeah, sometimes.
Because a lot of people's careers, like maybe, if you're just an engineer, you're shipping projects every year. But in your case, like let's say imagine you discovered P equals NP or something like that. Yeah, how do you feel when you make those discoveries, those sparse discoveries in your career?
Well, it's great. Yeah, it happens. The big ones happen rarely. I think of science, realistically, science and math is a community of ants work. Most progress we have these conferences, theory conferences, Stock and Fox, and then we have all sorts of satellite conferences, and there are hundreds of papers in them. Satellite, I mean, focused on a concrete area, and learning theory, crypto, online algorithms. Usually there are many, there are 1,000 researchers working in this, I don't know, maybe. And they are producing many papers a year. And most papers are, and most of my papers are, we make a little progress in understanding something. Usually it's not a big problem. We discover a variant of a technique, or we can strengthen a bound on some. And I find this essential. I think this is true in science in general. And bigger understandings come more rarely. And they suddenly, they send this shockwave to everybody learns them and uses them. But of course, those bigger understandings, it doesn't have to be a resolution of a 50 years old paper. It can be something that, when Barrington discovered his algorithm for counting that I mentioned, he was trying to actually prove that it's impossible. And it was not like somebody asked this question. The answer was obvious. It's impossible, right? So when you have an insight of this type, it's amazing. So whenever you realize something really new for you and for the community, is a phenomenal result. It's rare. I tell all my students and postdocs that, it's not, you don't work for the $1 million. $1 million is nothing, of course, for some of these problems. But you work because you enjoy the practice of it. You enjoy thinking about these problems. In fact, most days in the life of my life, mathematician's life, is unlike a systems person. You go in the morning, you come back in the evening, and you fail to do what you wanted to do. You just couldn't. You just thought more, and And I think that it's really important. It's not for everybody. Clearly, it's not satisfying if this happens every day and every week, and it's not for everybody. But it's for the people for whom this activity of trying to think, of throwing ideas, of failing but learning from the failures. People don't realize that often you learn. I mean, the fact that you failed is not just a wasted day. There is something that you gain from it, maybe subconsciously, that will help you later. So unless you enjoy this activity, maybe this field is not for you. And then you see something, and that, even if it's small, sometimes it's very satisfactory.
Last question for you, and I think people in the field might be curious because you have so much experience. Is if you could go back to the beginning of your career when you just started, becoming a researcher, is there any advice that you'd give yourself?
I think I was lucky enough not to think that I would change anything. I think I was lucky enough, and many people are lucky in this field because the field is so accommodating to young people. It's completely leveled. There's no hierarchies. People would go to conferences and meet. I remember my first conference meeting 𝗲𝗍𝗄, who was a god in the field and invented, did all these NP-complete things. And I was a first year graduate student, and somebody introduced me to him, and he immediately asked me what I'm doing. And I said I proved that some problem was NP-complete, and he was actually interested. He amazed me. I was lucky to have phenomenal mentors as an undergrad, as a graduate student. I was lucky to have unbelievable collaborators over the years, and you learn from all this. So it's not a very informative advice to people to tell them to be lucky. I think this environment exists. I think that one piece of advice I give everybody is that in the early stages is to work on things they enjoy the most. So when you are discovering your talents as a researcher, one direction may be, these are hot problems. If you solve them, then but maybe that's not your problems. Maybe it's not your affinity to them. You have to experiment with the type of problems. It's good to have a variety of areas and papers to read in these areas or problems to understand. It's always good to start with a few to sort of better understand your capabilities. And often what you like most is what you are better at.
Thank you so much for your time, Avi.
Sure,
I really appreciate
pleasure.
it.
Yeah.
Hey, thank you for watching this podcast. If you liked it and you want to see the show grow, please support with a comment or a like. Also, if you have any recommendations for people you want me to bring on, please drop a comment. Guests like 𝗪𝗏 Liskov, Mike Stonebreaker, Mark Brooker, these were all people that I brought on because someone left a comment. On another note, aside from the podcast, I'm working on building the ergonomic keyboard that I wish existed. Here's a glance at the prototype. It's a split keyboard, so there's two sides. This is in the case. But yeah, we launched on Kickstarter and we hit our goal within 8 hours of launching. I really appreciate it if you were one of the people who grabbed one of the early units. We're now working on the long journey of building the tooling now. And so if you still want to pick one up, I've left the late pledges open on Kickstarter, so you can grab one there. I'll put a link in the description. Thank you again for watching the podcast, and I'll see you in the next episode.